In our previous lesson, we had explained the Ohm's law and we also introduced the term resistance, which we defined as the property of the material to resist the flow of charges. In our this lesson, we'll talk more about resistance and we'll also explain the factors on which resistance depends. Consider I have an open circuit. If I connect a wire across the two terminals, for applied potential V, I'll note down the value of current. Now, across the same two terminals, for the same given battery, if I connect a wire of twice the length, again I'll note down the value of current. I find the value of current has gone down to half. So, applying the Ohm's law we learnt in our previous lesson, that is V equal to IR, where V is the potential, I is the current and R is the resistance. Now, keeping the value of potential a constant, we find the value of current has halved in a circuit, thus the resistance has doubled. Therefore, we observe that on doubling the length of a wire, the resistance also doubles. Therefore, our first inference is that resistance of a metallic wire is directly proportional to its length. Now, if I remove this wire and connect a wire which has the area of cross section twice of our original wire. In this case, when we calculate the value of current, we find the current has doubled. Again, applying the Ohm's law V equal to IR, where V is kept constant, the value of I doubled, the resistance is half of its initial value. Therefore, we can say on doubling the area of cross section of the wire, the resistance drops to half of its initial value. Thus, we get a second inference. Resistance is inversely proportional to the area of cross section of the metallic wire used. Now, combining the two inference and inserting a proportionality constant rho, that is resistivity, we get the dependence of resistance on length of the wire, area of cross section of the wire and resistivity of the material in the form of an equation R is equal to rho L divided by A, where rho is the resistivity of the material, A is the area of cross section and L is the length of the wire. Resistivity is a characteristic property of a material. The value of resistivity is low for conductors and very high for insulators. So, till now in our lesson, we have learned that how geometrical dimensions of a current carrying metallic wire can affect the value of resistance. But in the everyday life, we generally use a combination of resistors. So, further in our lesson, we will see how we can use Ohm's law to calculate the equivalent resistance of a circuit. By equivalent resistance, we mean how can we replace all the resistors of a circuit by one single resistor. Resistors can be connected either in a series configuration or a parallel configuration. The resistors can be connected only in these two configurations. So, first let's explore the series configuration. If the resistors are joined end to end and the same magnitude of current flows through the resistors, they are said to be in series. Let's calculate the equivalent resistance of resistors connected in series. Consider three resistors connected in series in the circuit shown. A battery of potential difference V provides a potential across each of the resistor. Let V1 be the potential difference across resistor 1, V2 be the potential difference across resistor 2 and V3 be the potential difference across resistor 3. Since the resistors are connected in series, a same magnitude of current flows through each of the resistor. Now, applying the Ohm's law V equal to IR, V1 is equal to I times R1, V2 is equal to I times R2 and V3 equal to I times R3. Also, V is equal to V1 plus V2 plus V3, where V is the potential difference of the battery in the circuit. Let V equal to I into R equivalent. Therefore, I into R equivalent is equal to I times R1 plus I times R2 plus I times R3. Therefore, R is equal to R1 plus R2 plus R3. Thus, for a series combination of resistors, we can say the equivalent resistance is equal to the sum of individual resistances connected in series. Now, let us consider the second case, where the resistors are connected in a parallel configuration. If the potential difference across each resistance is the same, and the sum of current flowing in each branch is equal to the sum of current flowing in the circuit, then the resistors are said to be connected in parallel. For the circuit shown, let I1 be the current flowing in resistor R1, I2 be the current flowing in resistor R2 and I3 be the current flowing in resistor R3. I, the current flowing in the circuit, is equal to I1 plus I2 plus I3. From Ohm's law, I is equal to V divided by R. Also, let I equal to V divided by the R equivalent. Therefore, V divided by R equivalent is equal to V by R1 plus V divided by R2 plus V divided by R3. Thus, 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Therefore, for resistors connected in parallel, we can say the reciprocal of the equivalent resistance is equal to the sum of reciprocals of the individual resistances. So, we have calculated the equivalent resistance for both the configuration. For a series configuration, the equivalent resistance is equal to the sum of all resistances connected in series. In a parallel configuration, the reciprocal of the equivalent resistance is equal to the sum of reciprocal of the individual resistance. A parallel circuit has many advantages over a series circuit. In a series circuit, even if one component fails, the entire circuit is broken and no component works. A very popular example of this are of the fairy lights used to decorate buildings. In a fairy light, all the bulbs are connected in series. Even if one bulb fails, the electrician has to check each and every bulb to find that fused bulb. On the contrary, in a parallel circuit, even if a component fails, current does not flow in that particular component. Rest of the circuit functions properly. Secondly, it is impractical to connect two components of different current requirements in series because the same magnitude of current flows through each component in a series circuit. Whereas in a parallel circuit, we can connect components of different resistance which require different currents for their proper operation. So students, let us quickly recap what we learned in this lesson today. We learned the dependence of resistance on length, area and material of the wire. We calculated the equivalent resistance of a series and a parallel circuit, and we also discussed how a parallel configuration is better than a series configuration.